Good morning. Today is May 6th, 2017, and this is the John Chappell Natural Philosophy Society Science Chat. And I have out here, I displayed some of our websites here. So I would invite you to check out and renew your membership if you haven't done that already. We also have a new wiki where you can edit information. We have already preloaded a lot of information on the scientists that we already know about. And we also have our forums where we can discuss things. And we also have Facebook, and we do have a conference coming up July 19th to the 22nd. So that's only about 2 months from now. I don't think we still have any registration information yet. Specifically on that, but you'll need to save the date. All right, so let's get things started. So let's see here. Who is here from last week? I think Mitch and Hans, and so I wanted to see what people thought of last week's discussion when we were talking about the magnetic field. So I was wondering, having to think about that for a week. Did you have any additional comments or epiphanies from what we discussed?
I have tried to prove in a theoretical sense the Lorentz force from principles that I take from my Wikiversity project, and I succeeded to do that, but it goes very deep theoretically, so it's not so easily to understand if you don't know a fair degree of mathematics.
All right. Did you want to give it a shot, or
if you can show if you can show the page? I think I sent you a message about it, and it's still there. It's on Wikiversity.
Yeah, I think so. You sent me a what was that, a PDF or something?
Yeah. I sent you an email about it. Well, I can put the address in the chat box if you want.
Let's see. Yeah, why don't you go ahead and put the address in the chat box so other people can see that as well.
I'm busy doing so. Help a book model. Yeah, go down. It's in the behavior of continuums page. It's about the quaternionic field equations, and there it is a section at the low end. I think it's about the Lorentz force. Yeah.
Okay, let's see here. I think I've got that. And yeah, you're right. It's all a bunch of equations.
Yeah.
So
a lot of equations, but
a lot of calculus.
There's a section below about the Lorentz force, and see what it is. Lorentz transform, force raising field, and there must be 1492 Lorentz force. I give you the pointer to it in the chat box.
Okay, so I believe I am sharing it. So can you see that? This is your section on the Lorentz force.
Yeah, it's
so
now as a pointer in the chat box. Open the chat box and you see there's a pointer to it. But yeah, you have detected it.
So at the very top, you start with Maxwell's equations. You've got del cross E and del cross B. So you have the electric and the magnetic forces equal to each other.
Yeah, but I use the quaternionic equivalent of the Maxwell's equations instead. It's a pure mathematical set, and it is complete and self-consistent. And the Maxwell equations are derived from observations. So you get then a mixture of the differential equations and physical units. That's the big difference between the quaternionic equations that you see here and the Maxwell equations that you see on wiki pages and what mainstream is using.
So I'm just trying to understand, first of all, so I guess as a result of our discussions, you decided you needed to go into explaining the Lorentz force formula. Is that correct? And you hadn't done that?
Yeah.
Now, the Lorentz formula is this like line 70, right? That's the Lorentz force law.
That's the end result.
That's the end result.
I started from the equations on the top of this section, equation 64.
Yeah,
which
64.
Is, the Maxwell-Faraday equation. You can get it in differential form. That's what you see in equation 64. And you can get it in integral form. And that's the next equation, 65.
Uh-huh.
It's the same thing, but one's in differential form and the other is in integral form.
Now, where does the force appear in this? Now that your first two equations in 64, there doesn't appear to be any force terms in
No. They come into the end as electromotive force. That happens in equation 69. Then you see for the first time an
69.
electromotive force. But in order to get there, you must manipulate a lot of with these integral equations. And for example, you have to apply the Leibniz integral equation in order to get there. It's quite mathematically, it's quite a complicated affair to get there. But if you do all these steps, then you arrive at the electromotive force, and then it's easy to go the next step into the Lorentz equation, which is the last equation in this section. That's equation 70.
Mm-hmm.
So it is not easy to do so. Also mathematically, if you understand a lot of these things, then
Hans, what system of units are you using?
None. It's completely mathematical. I use quaternionic differential
equations. What system of
equations.
units are you using? SI units?
It is no. It is the units are in the mathematics. So I'm not using physical equations. The physical equations are observation equations, and they use physical units.
So you're not using any units at all?
I do not use any units at all. That's right.
Okay, so what is B?
B is an equivalent of the magnetic field. And E.
What's the definition of it? What is it in terms of units?
In terms of units, it's just a part of the main differential equation. Then you have to go to, I must look it up. The B is defined in equation 7 of the same page. There, B is defined just as a mathematical equation, as a mathematical definition. So it has no units, and it is a part
well, you
of.
have to have some kind of units. I mean,
I mean, I think you could use any unit.
System of units.
Unix make no sense in it. It is just a relation between numbers. Numbers and quaternionic numbers and quaternionic functions.
64.
Let's say 64.
Equation 64.
That's the basic. That's the basic Maxwell Faraday.
I have no idea what that is. What's equation 64?
Now then start. Franklin, can you go up to equation 3?
Equation 3. Okay, we got first order partial differential equations.
That is the equation that shows how to you can compute total change.
Oh, well, you're using quaternions in here.
Yeah.
Okay.
This is a purely
So
quaternionic.
this is completely different from anything you're going to see in a physics book. As soon as
That's
you're
true.
talking about quaternions. Okay, I understand you're talking about quaternions now. Okay, so where is H? Where is the magnetic field? Where are you defining what the magnetic field is?
The H is very close to what B is defined. I'm not using H in this set of equations. I'm
Why
using
aren't you using
E and
H? That's
B.
what a magnetic field is.
Yeah. So the H and B mainly differ in their physical units. For the rest, it's quite similar.
Let's see here. We're getting quite a bit of noise from somebody here. So if you're not speaking, please make sure to mute your microphone.
I use subfields that are defined in equations 6 through 8. That are the fields that I use. I defined E, and I defined B, and I defined G.
What's G?
G is a kind of current field. How you call it? Current field? It's current.
All right. What is the basic curl equations look like?
They are parts of equation 3 that Franklin just showed you. This equation contains 1, 2, 3, 4, 5 terms, and you combine them. The first 2 terms are generating the real part of the equations, and the next 2 are defining the E field, which is a vector field, and the last term is defining the B field, which is the equivalent of the magnetic field. That's the curl term. They are sitting together in one equation.
And where is that?
It's equation 3 in the page that I hope Franklin has still available. I'm now looking at 2 pages at the same time. Franklin has still it up there. It's equation 3. It's you have on the top you have 2, and somewhat lower you have equation 3. And it has on the right side it has 5 terms. The 2 first terms are somewhat later defined as E, minus E, and the first 2 are defined as the real part of the field, and the last 3 terms are forming the imaginary part of the field, the vector part of the field. And the vector part of the field, these 3 terms, the first 2 of them are combined in E, what is going to be the electrical field, and the last term of these 3 is going to be the magnetic field, and it's defined as B. And that definition is done in equations 6 through 8.
So why are you defining the electric field as E and the magnetic field as B?
Because they are different things. They are
Well,
different
I already know
parts of the
that.
complete change equation.
You're saying B is magnetic field. It should be H.
Yeah, and your interpretations, as you're normally used to do, yes. But the biggest thing between B and H are physical units.
Well, not exactly. They're different things.
Yeah, I have to look it up to be precise. I never used H in my equation.
Well, that would be, you know, that would be a point of, uh,
Nomenclature.
I'm not really sure why you, it sounds like you just assume that, and I guess you can if you want.
Yeah, I'll try to next time. I'll try to have in this set of equations. I will introduce H as well, so that we can precisely talk about the things that.
My other question would be, what do you, how are you handle D? How do you handle electric displacement?
That is a similar thing. I haven't defined these things.
Okay, all right.
This is Bill Lucas. I have two questions also. Magnetic monopoles were definitely proven to exist in 2014 and have been reconfirmed by many papers, including one I just published. And if you'd like a copy, I can send it to you. It's on the experimental discovery of magnetic monopoles. But the other thing I want to point out is your force equation, besides not including the contribution from magnetic monopoles, does not have the acceleration terms that include emission and absorption of radiation, and it doesn't have the dAdt terms for radiation reaction. So it's an incomplete formula. It isn't practical. It can't be used in an accelerator or in any other place where you do experiments like that. So you need to take into account magnetic monopoles, and that means you have, besides Q for charge, you've got a magnetic charge you got to include, and then also you don't have enough terms. If you use all the equations, the empirical equations of electrodynamics, you get the acceleration terms and the radiation reaction terms for, so you can describe completely electromagnetic phenomena. But what you have misses a great majority of the electromagnetic experiments that we do.
Hey, Bill, can you put that link to your magnetic monopoles up on the box on the side?
If you'll send me an email, I'm on this email for this thing. I think you can see all the other people there. Is that right?
Well, you can type stuff directly into the chat, and you can share stuff that way.
Well, if okay, I'll give you my email in the chat, and then if you send me an email, I'll send you a PDF of the paper that was published in the Common Sense Science newsletter.
Okay,
so my email is.
I'd be very skeptical about a magnetic monopole, and how would you tell is North Pole, South Pole?
I have the experiments in there. You can do them yourself.
Okay.
I do it with, I use a compass, and I use bar magnets, U-shaped horseshoe magnets, and disc magnets, and all three confirm that magnetic monopoles exist. Then I send you, there's a link in there to a video where a person makes magnetic monopoles right in front of you by putting two magnets together, freezing them down to liquid nitrogen or helium temperatures, taking them apart at that temperature, and you see that both are monopole magnets.
Okay, well, I would
very
definitely
interesting.
have to
Just
see
like
that one. So please put the link up.
Yeah, I'm putting the link up right now.
But I mean, just to cut to the chase, I mean, that's basically taking two magnets and gluing the north poles together so that only the south poles are exposed. And that is what is basically being called the monopole.
Yeah, and it's not a possibility from what I can see, but I'll have to see the experimentation to.
But in any case, so I'm sharing the wiki on magnetic fields. You can figure out what the difference is between B and H is. And so I'm still a little bit confused because they say the term is used for two distinct but closely related fields. So I don't know how a magnetic field could be two distinct things, as I think it's only one thing. They're denoted by the symbols B and H, where H is measured in units of amperes per meter, and in the SI, whereas B is measured in Teslas and newtons per meter per ampere.
The difference, Franklin, is that you take into account the media that you have. One set of equations assumes you have a vacuum with no effect, and the other one says you have a media, and so B equals mu H, and the mu takes into account the media, and D equal epsilon E, and the epsilon takes into account the media for the field. So that's the difference between the two expressions there, or two.
So are you saying H doesn't take into account the media? Which one takes into account the media?
Well, B equals mu H. Mu takes into account the media, so H is assuming there's no effect of the media, and B tells you what the effect is.
So H is the magnetic field in vacuum.
With no contribution from the vacuum. No
Yes, with
effect.
no contribution. And
So
B
would include the effect of the vacuum.
Now they're saying that B is most commonly defined in terms of the Lorentz force. So that's the term that would come out of the Lorentz force law then?
Well, the Lorentz force
Or
law,
used in the Lorentz force law.
Isaac Newton said that you can't just go by one empirical equation. You must use the complete set, or you miss part of the information that's embedded in the empirical equations. It's kind of like if I have 4 simultaneous equations and 4 unknowns, and I don't use all 4 equations, I don't get every bit of information about the 4 unknowns. I have to make approximations to get a solution. And Maxwell only used 4 of the 6 empirical equations of electrodynamics. And if he had used all 6, and if Heaviside had used all 6, they would have gotten a lot further along. But they didn't do it. And also, Maxwell's equations do not conserve energy. So that's something that, and they don't satisfy Newton's third law. So there's a lot of stuff that the way Maxwell did it is bypassed. But if you do it properly according to the rules in Mathematical Principles of Natural Philosophy by Isaac Newton, you will get all the full solution.
Okay, well, I want to ask Harry. So, Harry, does that clear up what the difference between B and H are? Do you still see those as being different?
Yeah.
Well, I don't really agree with what Bill said. Is in the kind of, if you want to think about it the way in terms of media, what he said is perfectly fine. I generally look at it in terms of B is quantity of magnetic field and H is intensity of magnetic field. And that's kind of, a lot of people don't really understand the distinction. And that's kind of the source of the confusion. That also occurs in the case of the electric field, E being the intensity of the electric field, and H is the quantity of it. And to really understand what that means is a bit difficult to express. So they're 2 different concepts.
It'll be a lot like the voltage and the current, right, Harry? The volume
Well,
and the flow.
let me sort of go into it a little bit. Voltage and current, um, you could look at it that way. In the older books, they sort of express it a little. It's easier to understand in the older books than it is in the newer books because they changed electromagnetic theory after World War II to sort of make it consistent with Einstein's theory and some other issues. So the older textbooks make a distinction between B and H much better. And what they did was they got rid of the magnetic pole after World War II. Before World War II, the textbooks talk about magnetic pole, which you could conceivably think of as Bill's magnetic monopole. So do you want to know the difference?
By the way, you can buy magnetic monopoles, but they're called magnetic unipoles.
Well, I'd rather not waste my money.
So Cornelius, to kind of explain it to you, you might want to think of the quantity measure of the field as the flux per unit area. whereas the intensity is the intensity of the field at a point.
Right. Yeah, I'm comfortable with that. I'm working with electromagnetics quite a bit in my job.
So do you quite understand the point I was trying to make there about the
Yeah,
intensity is measured at a point, whereas the quantity is measured over an area?
I understand. Like I said, it's just a lot like current and voltage.
My aim is to analyze what happens at quantum scale. And at quantum scale, you are not confronted with the medium with material, with solid materials in the environment. H exists in a solid a medium in an environment, and B exists also at the in the environment of effect that what constitutes the electrons and what constitutes quarks and all those things. In those environments, things like E and B exist, and H and D do not mean so much. So my target field is to investigate what's beneath the skirt of the electrons, I would say, and the fields are defined in terms of E and B.
Well, I find that kind of confusing because at the quantum level, I would think that you wouldn't want to have B at all. B is a measure of quantity of magnetism per unit area. Okay. And so if you're talking about the magnetic field at a point affecting an electron, you have to talk about H.
Electrons, yeah, you have to go into my model to understand it completely. But electrons are
Well, the
point-like objects.
point is that if you're dealing with a point-like object, you can't use B because B is a measure of field per unit area, and you don't want it per unit area. You want the intensity at a point.
No,
If
B,
your objects that you're dealing with are point-like objects.
B is not defined in terms of units per unit of area. It's
Yes,
a
it is.
curl.
I'm afraid
It's
it
a
is.
curl of a more basic field. That's the definition. That's the definition of B.
Okay,
And
well, you can define it wherever you want to. But it doesn't make any sense to me because B is field quantity per unit area. And so now you're talking about B, which is a quantity per unit area acting on a point. I don't see how that works.
The definition you have for B equal del cross something is only that valid if mathematically if there are no magnetic monopoles.
Yeah.
That's right. So
Right.
the existence of magnetic monopoles will discredit your work.
Well, it doesn't discredit it because it's a purely mathematical setup. And I used the property of the quaternions, the multiplication property of the quaternions, which is stated in equation 1 of this set of equations. And instead of the first factor, I have put the nabla. And if you do so, then you get the equation 3, which is no more than the multiplication rule between the nabla operator and some field uh, uh, used in a similar sense as two factors that are multiplied in quaternion function theory.
But you see, the quaternion equations that you're making
That
are
is,
dependent on whether magnetic monopoles exist, and they're assuming they don't.
they are not occurring in these equations. So
That's right. So they're missing something, and you're trying to make a mathematical solution on something that's mathematically incorrect in terms of not including all the
It's
physical
only
phenomena.
incorrect. It's only incorrect if you want to encapsulate these monopoles in it, but the monopoles do not exist in these equations.
Also,
you
the
start
quaternion equations do not satisfy conservation of energy or Newton's third law.
There is a
And
conservation of energy, yes.
they don't do conservation of energy. It's not a part of Maxwell's equations in the quaternion form or in Oliver Heaviside's vector form. That has to be added separately.
Maxwell equations are not complete, but the quaternionic equations are complete. It's a complete set.
Bill, could I ask you a question? This is Harry.
Yes.
When you talk about a magnetic monopole, are you talking about a magnetic charge, which is a point source?
Well, first of all, the equations of electrodynamics, the empirical equations, are not microscopic equations. They are macroscopic equations.
You're
That's why
talking
you
about
have
Maxwell's
D equal
equations now,
epsilon
right?
E and B equal mu H, because it's macroscopic. And so if you look at the what magnetic experiments you can do on the macroscopic scale, you can make magnetic monopoles. And so now, if I ask the question, what is charge? Maxwell and Faraday and all these people have to say, I don't know. Just like when Newton was asked, when he wrote down F equals ma, and he was asked, what is mass? He had to say, I don't know. And when he wrote down his force of equation, F equals big G m1 m2 over r squared, and you ask him what was mass, m1 and m2, he said it's the property of each of the particles, but he didn't know what it was, so he represented it with a constant. And so that's the problem we have. We haven't defined these things. Now, the definition of them was discovered by Arthur Compton, and he received a Nobel Prize for that. And his last graduate student, Winston Bostick, went further than Compton did, because he showed that elementary particles can be created entirely from the field. The particle doesn't create the field creates the particle. And so all the properties we're assigning to a particle, mass and charge and everything, are approximations. They're not real, because you can show that the elementary particle is entirely made of fields.
Bill, I advise you
Bill,
to take a look at the.
Are these magnetic monopoles points? Are they point sources or what? That's what I want to know.
I think could we have Bill share that site, and maybe we could just bring up the information on magnetic monopoles and look at that directly here. Because
Yeah,
I
we
think
can
that seems
do
to be
that. That would help in the discussion, I think.
it really would.
I don't have my paper here, but you want to see a video on magnetic monopoles? I'll get you the reference
Well,
here.
I was looking on eBay, so you can find these things on eBay. So, but I'm looking for the term. It's not the unipolar magnet or monopolar magnet. What do they call these things?
Well, the sites I was looking at, they're in India and China, where they make a lot of the magnets that we use. Those
Yeah.
companies call them unipole magnets.
Unipole magnets.
Yeah.
Yeah.
And
Let's see if we can find that.
and they tell you how they make them. And what
If
they
you
do,
got that
most
video,
magnets are made by sintering. In other words, you take some material that can be magnetized and you heat it up, you put it in a mold, then you put a field on, and then you let it solidify. And then you end up with a certain magnet with a certain orientation of the field.
I think that's the process that Franklin described last week.
And but anyway, let me see if I can.
Bill, I'm still looking for an answer to my question. Is the magnetic pole a point source?
Magnetic. No, the charge is not a point source. Neither is a magnetic monopole.
We got a big echo going on here.
Well, I just said basically since,
That was Ed.
particles come from the field, basically, yeah, the source is not the point, but the field, right, Bill?
Yeah. Okay. I have a reference here. I'll put in the chat. It's a video on how to make a monopole magnet, and they do it right in front of you and on the camera, and you can see what they do, and they measure and they test it and they do all that kind of stuff. So I'll put that on my chat here, and you can look it up.
All right. But now I think the question really is, if you take two magnets and you glue the south poles together, such that only the north poles appear on the outside, is that a monopole magnet? Now I would say no. I would say that's not a monopole, as the other opposing
Well, you
field
can test that.
appears inside.
You know how to test that?
Well, you can't really glue them together anyway.
Go around and see if there's only one field.
Yes, you will see that there's only a south field emanating.
There's going to be more than a south pole.
But the north pole has been hidden on the inside, so I don't necessarily. I personally don't consider that a monopole.
Well, you couldn't really hide the north pole on the inside by just gluing two of them together.
We know experimentally to determine.
No, you can. You can totally hide the north pole.
Monopole is by either using iron filings around it or using a compass, so we can see the actual field.
Well, if it's a monopole,
del dot B equals 0, that's in the Maxwell's equations, says that all magnetic fields have to occur in a loop. They cannot be going out all in one direction. So anytime you have any field that goes out in one direction that the compass only sees in one direction. By the way, I've got all this experiments and everything recorded in my paper. So if you send your email to me, I'll send it to you later today.
A true magnetic monopole, those iron filings would have to be pointing in straight lines directly out from the center of the sphere.
That's right. And you don't see that on when these magnets are put together the way we were talking about. You have to either freeze it and then take them apart and then look at the fields that are associated with it, or you have to do what I do in my experiments. I put a iron disc in between two magnets, and when I put the two magnets, let's say the two bar magnets both have a north pole against the disc, they click together, which is very interesting. Why would they click together? Because normally north and north repel, and so when they click together, then if you measure the field coming off of that iron disc that's in between, you'll discover it is a magnetic monopole.
No, you'll discover it's not a magnetic monopole because you've got the edge of the north edge of the field going around to the two south edges of each pole. That's not a monopole. That's two north poles.
You have to look at the whole field around the whole setup.
Around the disc
is the fields coming off the central disc do not join to the fields on either end of the magnet.
Yeah, they do.
There's other fields that do. So,
Yeah, they do. We'll have to look at the video. I have to see the evidence because
so anyway, let me get this.
it's quite clear that they would go to the North Poles on the end of the magnets.
Let me send you this thing out here. I've got to get it down.
Yeah, right. Put the video in there. I'll go get my magnetic monopoles.
All you really got in a case like that is you've got a North Pole. If you put the two norths against the disk, you've got a North Pole in the center that's emanating from the disk and radiating outwards from the disk directly, but it curves around and goes back to the South Pole at either end. And in that one plane of the disk, you have magnetic field lines that are all radiating outwards, but they're radiating outwards and they're spreading out towards either end. It's not a monopole.
Okay. I just put
There is
the
a loop of current
chat
there.
up, and if I made a typo, you just have to do a search on how to make a magnetic monopole in YouTube, and you will get it. But I put the whole reference there for you.
Okay, let's have a look at this video here. Just a second here. Let me share this. First of all, let's skip past the ad here. This is a little bit long, 5 minutes, but let's see. I gotta share this. Okay. And let's see, I need to put my microphone.
Is it starting?
Is nothing happening or who's talking?
I think everybody's still watching the video. I don't know if we're done yet, but it is a interesting video. The explanation is quite easy though, but it doesn't really show what happens when he moves the north or south poles to the rim of the same
I
magnet.
don't see any video at all.
You had to click on the link and actually look at it on your own computer, I think. I don't think Franklin is sharing it. If you are, it wasn't showing up. So basically, I think each individual person was looking at the link themselves. Is that correct?
I'm looking at the link. In the paper that I will send you by email, I do my own experiments with compasses and that sort of thing. So it's different from this experiment.
Can somebody tell me how to
I-
find this link? Where's this link?
It's in the chat.
Where's the chat?
There's a box at the bottom. It has a little. If you click on it, it brings up the chat. On my screen, it's right next to the meeting notes. See, we still
Where's
got
the meeting notes?
At the bottom of the screen where you have your microphone and your camera and that. The second icon from the right would be that chat icon. If you click on that, it should open the chat window.
I see a bunch of boxes at the bottom representing all the participants. I don't see anything else at the bottom of this app.
Okay, well, you have a different app than I have.
It's below that. It's the part that shows your microphone, your camera, the share, and stuff like that.
Yeah, this app, I just downloaded this. This is a Fuse app. I just downloaded it, and I see nothing like that.
Okay, Bill.
If you
So
go
I
to
can-
YouTube and put in the request or the search for the search, how to make a magnetic monopole, you will get a number of videos, and the top one is this one. There it is.
Franklin, I can't hear you. You seem to be talking, but no sound.
Can you hear me now?
Yes?
Okay, my microphone was unplugged. Okay, so do you see the video now? Do you guys see the video?
It was started, but then it disappeared.
Yeah. Well, it disappeared.
Yeah.
Well, if I start it now, do you see it?
Not on the screen.
Did you guys see it on the screen? Is it sharing?
Momentarily, we saw the screen.
Because it looks like when I play it, you can see it, but when I pause it, you can't, which is kind of weird. Well, do you see, I should be sharing my whole browser screen here with YouTube. Do you see that?
No.
No? Let me see here. Let me share my entire screen then.
There you go.
Okay, so do you see that? You see my entire browser screen now, right?
Yes.
All right, so let's go fast forward the video to the very interesting bit, which is that he freezes Let's see. Someone's going to have to mute. I think that's you, Ed.
All right.
Okay. I'm still getting a huge echo. I'm going to have to go out and mute you explicitly. Okay, I think we're okay. Yeah, use headphones. That works better. Okay, so he explains that he takes the magnets when they're attached and he freezes them, and then he takes them apart, and then he's showing that one magnet is only attracting one pole. So this is okay. Well, that's what the magnet normally does. The magnet normally, when you flip it over, it changes poles. Okay, that's what it normally does. Okay, so after he freezes it, and he separates them, then he goes. Then he shows that okay, so no matter which way he flips it over, it only attracts that one. Okay, so that's the demonstration. And that is not, that's not gluing together two magnets to make a monopole.
I think the key to this might be that if you were to, instead of flip the magnet over top to bottom, if you were to flip it left to right, the opposite pole is on the edge of the magnet, and like the north would be in the center and the south would be on the outside edge of the magnet. When he freezes it and rearranges the magnetic domains within the magnet.
Well, freezing freezing should not rearrange the domains in the magnet. I mean, looking at this, I'm extremely surprised, and I would say that what he's showing is actually impossible, and that what we're looking at is actually a trick. It's a fraud. It's a YouTube fake news, but it could be true. I mean, it looks true, but that would be my first reaction, that this video is fake. Although it's very difficult to do what he's demonstrating, which is to take any magnet, especially a neodymium magnet, which is powerfully magnetized on its axis, and then make it do what he is showing, which when you flip it over, it does not cause the compass to flip the other way, like he showed before.
I don't know
Look a bit further. Look a bit further in the video. There he shows another thing that's interesting.
Yeah, I don't think this is necessarily a neodymium magnet because they're really not strong enough. From the indication, they really don't seem to be that strong a magnet. If they were neodymium magnets, he would have a terrible time pulling them apart, as he demonstrates later on, where he slides them apart. That would be a lot more effort than it is.
No, that's consistent with what I've experienced with neodymium magnets.
Maybe so. I've got some neodymium magnets on my desk, and you cannot pull them apart like that and slide them apart anywhere nearly as easily as that. I've got a good blood blister on my finger from where I got my fingers between two neodymium magnets just yesterday. You don't want to do that. They're strong.
So the question is, is this real, or is there something fishy going on here?
I believe it's possible.
My comment would be, this is Harry Ricker. My comment would be, he doesn't show us what the magnetic field looks like. There's magnetic field ways that you can look at the magnet with different types of films, and there's magnetic film observing devices, and we don't see any of those being used here. So, without that, I don't know what's really going on.
Well, what I do is I use a whole lot of compasses. So I get measurements all around it simultaneously. And I do.
Do you know what a magnetic field viewer is, Bill?
Yeah, they're not very precise. Compasses are better, I think.
Well, yeah, you have a better idea than looking at the compass.
The other thing I do is I take the field at the edge also. He is just looking at it top and bottom, but I go all the way around the edge, and I show that when you have a disk magnet, you have both a north and a south on the edge. And then when you make a monopole magnet, it's only a north or only a south all the way around the edge of the disk. He doesn't.
Right, but if you have a north on the edge, then it's a south in the middle.
No, it's north in the middle too. But
Okay,
anyway,
that,
you need to be able to show all of that. He doesn't show the edge as well as the front and the back, or the top and the bottom.
do-
You have to show all three-dimensional. You have to show it three-dimensionally that it's going out away or toward the magnet. In other
well,
words,
if you have
I
a
think
true
that- I
monopole
think that
magnet, you
really,
ought to be able to make it out of a sphere.
it should be you could, in principle, make a sphere. Yes.
I think you need to get a magnetic field viewer.
Yeah. So, Bill, do you have actual photos of your?
Yes, they're in my paper, which I'm going to send out.
Okay,
So,
thank you.
Bill, but you're not using a magnetic field viewer.
No, because the magnetic field viewer can be affected by many things besides what you think you're looking at. But yeah,
Well,
you
I've
could,
never-
in
I've
principle,
not
do it.
found that
That's
to
the
be
same thing
case,
as
Bill.
using iron filings, except that,
I'm not found that to be the case.
well, that's my experience.
I'd send you mine, except for mine doesn't work very well.
Did you use any iron filings in any of yours, Bill?
No, because my magnets were too strong. the, the magnetic
Okay.
filings, you need a weaker magnet for magnetic filings. Um, and
Okay.
but my compass was very sensitive. And but yeah, I haven't done, but I'm planning to try more experiments. I'm not through. I just got the first round done, I guess you would say.
Now, did you also freeze the magnets?
No, I didn't do that. I
Okay.
tried to. I called my former mentor at University of Maryland, and he has a laboratory there, and he has liquid helium and liquid nitrogen. And I explained to him the experiment I wanted to do, and he was afraid to do it because
So,
he would get fired.
but your paper isn't up there anywhere we can get a link to. We'll just have to ask you for a copy of it.
It will be up on the Common Sense website, Common Sense Science website, but it's just in the process of being published. I have finished editing the newsletter, so I just send you a PDF of the newsletter.
Okay, I'll send you my email address and ask for that. Thanks, Bill.
Sure.
Bill, how do you define the magnetic field then? For example, in classical electrodynamics, it's defined as a curl of current density, gives you an A field, vector potential field, and you take the curl of that, that's the B field.
Right.
How then do you define in that kind of mathematical language what a magnetic monopole is? Because apparently you wouldn't be able to define it using a current loop.
If you send me your email, I'll send you a copy of the paper, and it has that in it.
Oh, okay. Thank you.
Well, I find that very surprising. So I find that video completely inexplicable. Since
Yeah.
I would say that magnetic fields only exist in the presence of a current loop, and as such makes monopoles impossible. But
I have an explanation for you. That
okay,
that clip where the north magnet was chasing the disk across the table, that was put together with several stills that made it look like an animation. You look at it, there were individual stills spliced together with some kind of photoshopping thing. That total deal is bogus.
So that may be possible. I'm not. If you look and if you do that same search, you'll find a number of other videos, but they're using all different kinds of techniques to make the magnet.
Well, they're using more techniques to make the video than to make the magnet.
Well, yeah, there may be. I mean, when you put one together like that and you edit it, you can do anything you want.
I mean,
You know what I mean?
things
So
that
look
I
at the
find.
video. The video is not smooth. The part there where the north magnet is chasing that little disc across the table, that's only 4 or 5 frames. It's not a continuous movie.
Bill, is it possible that you could possibly set up something for next weekend to demonstrate for us online any of your experimentation?
Well, the paper, you can reproduce what's in the paper, but my problem is I took these pictures with my digital camera, and I'm having trouble using, like when I'm using a 2 bar magnets, and I put in a steel disc between them, um, and I make a monopole. I have trouble measuring with my compasses the fields around that with the presence of the bar magnet. You know what I mean? And so the only way I've been able to do it really well is with the disc magnet. And but you can see I took pictures with my camera, and I didn't fake anything. That's what you really see. And
Sure.
but maybe I didn't do everything that could have been done. That's a possibility.
Okay.
Okay, got to be humble. You can't say everything. But I also reference many other papers and institutions that have claimed they have made magnetic monopoles, and their papers are published in the regular journals starting
Yeah.
in 2014. So 2014 was the first year magnetic monopoles were claimed to exist experimentally.
So I'm looking at this video and I'm never seeing him put the North Pole next to the center magnet and next to the edge
Well,
of the
that's
same magnet at the same time.
when you make these monopoles and you put 2 of them together, you lose the monopole.
Yeah, but I mean, earlier in a section it was just showing a second ago, and he was pushing the North Pole against the magnet, and then he flipped the magnet over and he pushed the North Pole against the edge of the magnet again. I'm never seeing where he's showing that very same magnet, if he moves the North Pole to the center of that disc, whether or not it's going to attract or repel. And I believe if he moved that same magnet to the center of the disc that he's got, that it would wind up attracting that North Pole instead of repelling it like it does on the edge. But he never really demonstrates that in his video. That's kind of missing, and I think that's kind of the hidden key as to how this particular experiment is working.
Now, what I found is when I put a steel disc between 2 magnets,
Correct.
both the north and south pole, and what I found is that if the steel disc is no bigger than in diameter than the magnets, they won't go together, and there's no magnetic monopole.
Correct.
The one in the center has to be bigger, and
Yeah.
so so that's an interesting. What that means is the field. If you thought that you had a north and south field in the disk, the field would have to be perpendicular to the fields in the other magnets.
Right, and I think it actually is
Well,
perpendicular. That's
that's
what
the
I'm
way it
saying.
is when they make a unipole magnet, but they put those magnets together to form a toroidal ring, and then anywhere you go around the ring, you can only see one type of field with a compass.
Correct. Yeah, that would be because the other field is in the center of the disc.
Yeah, then it doesn't come
Okay.
out.
Yeah.
It doesn't come out. So
Well, it does
you
come
get to
out
a
through
point
the
where you
end
can
of the
see it.
magnets you got attached to it. So.
Yeah.
But
So
let's look at your paper. I'll look at your paper. It'd probably be better than just going on too much about hypotheticals or
right.
trying to get visual
I think
images
this
of
is
it.
a good way because you can look at my paper, you can critique it, you can ask questions about other things, you can actually reproduce a lot of the experiments, and but that was my goal. And I also quote other papers that have been published, but they were not doing magnetic monopoles the way we would want to see them done. In other words, they're doing spin ices and all kinds of exotic things, which we don't have the equipment to reproduce.
Have you seen a demonstration of putting 2 monopole magnets in, say, a test tube or a tube, and watching one support the other? One will float above the other. Have you ever seen that that would be an obvious experiment to run. Have you ever seen it?
No, but I think that if we could reproduce, see, I'm trying to reproduce what we saw in that video. And but when I went to the laboratory, the faculty member there at University of Maryland, by the way, if you don't know it, University of Maryland has the world's largest physics department, over 300 full-time faculty. That's the most as many colleges have for all the fields put together. But anyway, they have over 300, and but in order to maintain your position there, you have to be very careful. If you do
Well, it
something
seems like they're more interested in instilling fear in their scientists than instilling a spirit of inquiry. If they're going to fire somebody for doing some experiment, but if you take that disc and you just magnetize it hemispherically, so you have the left side of the disc north and the right side south, you can push that along the table as long as it doesn't spin around. So there's lots of ways of doing that. There's lots of ways of doing a
right,
demo.
but with the compass, I can show the field all the way around the edge, as well as the field on each side. And so that's what I like about the compass is I can do all that simultaneously.
And you've done that personally.
Yeah. And so, however, it's hard to photograph it. I need some suggestions on how to get some of that photographed properly. And so
that would be a really good demo if you could do that. If you can also suspend one monopole above the other one.
well,
we've got a little device that does suspend magnets.
You'd have to have a tube or something, so that it won't fall apart. Slide off the hill, sort of the.
Have you seen a spherical monopole magnet?
No, I haven't. I don't have any spherical magnets at the moment. Most of mine are either bar magnets, horseshoe-shaped magnets. I have some elliptical magnets, but they're not very useful. and then I have disc magnets.
Yeah, I think what this guy is using in the video is probably just a plain piece of steel that's been magnetized. I don't think he's really using.
That's where how I make my magnetic monopoles is in a piece of steel where I'm I'm magnetizing it.
Yeah, so in other words, your magnetic domains are easily rearranged in that piece of steel. You can easily, and so that's what's happening here is they are rearranging the magnetic domains in that steel.
And I show that the geometry of the magnetic monopole or unipole has to be a certain way or it won't work, even though you've got the same materials. In other words, if you make the disc between the two disc magnets, if you make the steel disc that's in between them too small, they just repel. They won't go together.
Correct. Yeah.
Well, I'm looking at the comments. I'm looking at the comments in YouTube here. So if you've got a fake video, people will usually try and call that out. So this guy, Zoomer1, says, this is a fake. He's just switching from axially and diametrically magnetized magnets off camera, which I can see happening. That's so he's using two different sets of magnets, which have been magnetized in different directions, because you can always orient the magnet so that it would be like pretty much all attracting. So I have like two neodymium magnets here, and if you stick them edgewise, they will continuously attract each other no matter what orientation you put them at, right? They'll be all attractive in that orientation, right? But they'll be either attracting or repelling if you put them opposing directly this way.
Right.
So I mean, other people mentioned that there's definitely lighting tricks, and they're definitely cutting different things. Although this guy seems to be going through an awful lot of work to come up with a fraudulent video here.
You can, with your little demo you just did, if you take 4 of those magnets and you put 3 around a central one, you can stick them so it looks like a little flower. And if you move one of the petals, the other 2 petals will move as well.
Yeah, to come to an equilibrium.
Well, I've got 4. So what did you want to do? I've got
take one and put it in the center, and then take three and put it around there. Put petals on the flower. Take one as the center and put 3 others around it.
The 3 others around it. Let's see.
So you got one in the center and three. You got three
Well,
satellites.
I don't know. They just want to make it
One in the
square.
center. One in the center and 3 satellites. You got 4.
But it doesn't
One
want to go
one
that
Earth in
orientation.
the center with 3 moons.
If you had more discs, magnets, you might be able to do it.
You take one in the center and you put 3 moons on it.
You have to put the one in the center with the north up and the other 3 with the south, with the north
Well,
down on the
whichever way it'll go. It'll tell
That's
you
the
which
only
way
way you're gonna. That's the only way you're gonna get the reaction that you're talking about.
You
The 3 outside ones have to have their poles all facing the same direction.
Okay, let's see it. So I've got.
Now you
there you go.
There we go. Got it.
Hold the center one, and then if you move the other one, the other two will move. They'll move around.
Yeah, like that.
There you go. Now you got you got something to analyze. All your north and south and all your poles. You got yourself a problem there.
Well, I'm more inclined to think that video is just fake.
I think he actually did it.
That would be my conclusion.
I think he actually did it. I just think he's got just a piece of steel that he's magnetizing and changing the magnetic polarity. And as he's cooling it and sliding it, you notice he also slides it apart, and that changes the magnetic.
I think that whole
the magnetic field within the metal as he's even sliding them apart.
Well, I think that whole cooling thing is a farce too, because clearly he didn't. The magnets didn't reach temperature cool enough to cause condensation, which means that basically the magnets weren't really cold. I mean, he was like wearing gloves initially, but clearly when he's demonstrating things, everything looks like it was warmed up to room temperature. There was no condensation. He's handling the magnets with his bare hands, which would have obviously warmed up the magnet. So all of that contradicts what he was saying.
What I didn't explain to you what I've done at University of Maryland. When I got my master's degree, I measured the magnetization of nickel from 2 degrees Kelvin to room temperature to 8 significant figures. And that was more than had ever been measured before. And there were 4 competing theories of magnetism in physics at the time. And so my work showed that only one of the 4 could agree with the data. And that was the theory of magnetism that you find in textbooks today. That was in the 1960s I did that. And so I have a lot of experience working with these very low temperatures inside dewars and double dewars and all that kind of stuff.
Yeah, but that experiment did not look like it was at ultra low temperatures, right?
Well,
you could tell that.
The first part where he had the gloves on and he took them apart, you wouldn't need gloves on if you had done something in your refrigerator. You would need gloves on.
It looks like he had done something in the refrigerator. I swear it was like, it had like water droplets on it, which means way higher temperatures than liquid nitrogen.
It means that it got warmer and it got the moisture out of the air. But what he was claiming was that he separated the magnets at low temperature, like 4 degrees or 2 degrees or 70 degrees Kelvin, and then he allowed it to warm up, and he could touch it with his hand then. But the magnet's not stable, and if you put it near another dipole magnet, it'll switch back to the dipole mode, and that's what he claims happens.
Yeah, but I think that's totally fake. This is example of fake science on fake eBay.
Well, the only way to prove it is to reproduce it, and that's what I wanted to do, and I'm still working on that.
Well, it shouldn't be that tough to reproduce, Bill.
Well, the laboratories.
You don't need a laboratory to do this. You don't need a laboratory.
Know me and have the equipment.
You don't need equipment. This guy doesn't have any equipment.
Low temperature. I don't have. Do you have 2 degrees Kelvin at your house?
I can create very low temperatures. I can create very low temperatures with Freon. Now that's not liquid nitrogen.
Freon doesn't get close to these temperatures.
Well, I don't think this guy is. Who has got coming all the noise? Is that whoever that is? Please mute yourself. Thank you.
The reason you have to go to a laboratory that has the equipment to do experiments at these temperatures, and I have only 2 that I'm acquainted with in the Washington area. One's at NIST and one's at University of Maryland. And,
if I really wanted to perform this experiment, I would take it to my local science museum, the Pacific Science Center who do liquid nitrogen demos every single day, and they throw away buckets of liquid nitrogen at the end of their demos. So I guess I could just bring my magnets over there, right? Say, can you put that in there?
Do that, and then take some gloves with you so you don't freeze your hand when you take them apart.
And I bet you when if I did that, that the magnet would do exactly what we see in the beginning of the videos, that when you flip it over, it flips the poles. I'm almost positive that that would be the result.
Well, that's
Of course, I'd have to do the experiment, but you know,
right.
I
yourself, because people can cheat on these videos.
yes, that's why I was looking for. There was some other guy who was making a response to that video, and you know, I was hoping that he was going to try and replicate that thing, but apparently he didn't. But you got to watch out for stuff you see on YouTube.
Yeah,
Really.
right. But
So,
if you also look, you'll find some more people doing a similar type experiment, but differently. And they're claiming magnetic monopoles also, and they're using them for these what are called free energy generators.
Bill, can I ask you a question?
Sure.
When the physicist talks about a magnetic monopole, he's talking about an elementary particle, and these don't have anything to do with elementary particles.
The assumption has been made in the scientific community, physics community, that the macroscopic equations of electrodynamics apply on the microscopic scale. That's an assumption. And but all of the empirical equations of electrodynamics were all done on the macroscopic scale. None were done on microscopic scale, one charge. And so, but there's a problem in, and this is what Paul Dirac pointed out when he developed quantum mechanics. The problem is charge is quantized. But the only way in the theories of quantum mechanics to have quantized charge is to have magnetic monopoles. If you don't have magnetic monopoles, it's impossible to have quantized charge. So there's this problem that the quantum mechanics has had, and the Dirac theory of quantum mechanics is the relativistic, most accurate version of quantum mechanics that we have. And so this problem that quantum mechanics has is still relevant. And if you go somewhere and find out what are all the problems of modern science, you'll find one of them is explaining the quantization of charge. And but there are many other problems too. And so that is a problem. And the people who first claimed in 2014, you'll see the references in my paper, and you can go online and get a copy of those papers. They claim that they're using quantum fluids and quantum ices and stuff like that, and they're seeing magnetic monopoles. And
who's talking right now? Who is that? Who is talking? Who has that paper?
This is my paper that I just sent you the link to.
Bill Lucas.
Bill Lucas.
Okay.
And if you
Thank
send
you.
me an email, I'll send you a copy of that paper.
Thank you.
But Bill, you still haven't answered my question. I mean, the point, my understanding is that they, based on what you said, that there was a prediction by Dirac, maybe I'm wrong in this, that magnetic monopoles existed as elementary particles.
No,
And
he
this
didn't
is
say
not
that
elementary
exactly.
particles that
What
we're
he
talking
said is that magnetic monopoles do not exist. You can't have quantization of charge.
magnetic monopoles as elementary particles.
Well, you see in quantum mechanics, the idea of an elementary particle is not part of quantum mechanics. The theory of elementary particles is another theory. Quantum mechanics is a way of describing a system such as an atom or a molecule or something like that. So you've got to remember that this idea of what is elementary is up in the air. Now, if you look at ancient philosophers before
But Bill, you're evading the question. I mean, my understanding is that when they were talking about searching for magnetic monopoles, they're talking about searching for some kind of elementary particle like that is part of what people talk about when they mean elementary particles. They're looking for something called a magnetic monopole.
That's
Correct?
what the people do in elementary particle theory. However, elementary particle theory has cannot explain a lot of things like the quantization of gravity and the and the quantization of charge. Those things are mysteries in elementary particle theory, and there's like 20 or 30 mysteries in elementary particle theory. And but what I'm trying to point out is if you go back in time to the time of Democritus and Plato and Aristotle, and then even before them and the Indian Jains, they believed that all matter was made of um, what they called monads, and the monads were uncuttable. They were the basic building block of all material. And they would say, they didn't talk about elementary particles, but they would say that any kind of matter, including elementary particles, is a structure of monads. And it's that structure that has the properties of mass and charge and magnetic monopole. That's what they would say.
But I still don't think that answers my question.
So anyway, there is no such thing as an elementary particle in the sense that you're trying to say. Why is the electron have a certain quantized charge? Why is it the same as a proton? Why is it the same as a negative pion or muon or kaon? And but why is it that the quark, which is the component of the neutron and the proton, why does it have charge of E over 3 or 2/3 E over 3? That means that the charge of the electron is not quantized, and it's composed of three things. You see
Well,
what
the
I'm
quark
saying?
is just,
There's a lot of inconsistencies here, and you got to see that because you can't just base your argument on one part of one group's view, which is not supported.
oh, but a quark is
Well,
an
my view would be that in the old days when you had Coulomb, the Coulomb measured the Coulomb's law between magnetic poles. You remember that?
Well, he used fields, yeah. So
Well, he measured you had Coulomb's law for electricity and Coulomb's law for magnetism, and he did these
all measurements
experiments
are
where
based
he
on fields.
hold on, where
Where do
he
these
verified
measurements
the inverse square law for between electric charges and the inverse square law between magnetic poles, which I'm not sure whether you're saying these magnetic poles that are in Coulomb's law are what you would call a magnetic monopole or not.
No, Coulomb's law needs to be corrected for magnetic monopoles. And if you get a
But
copy of my paper,
Coulomb's law is for magnetic monopoles.
if you send me your email, I will send you a copy of this paper, and in there I show you how the various laws are changed with in terms of the formulas when you have a magnetic monopole.
So if I have a magnet, according to what you said before, the field spreads out uniformly in all directions, right?
That's right.
So therefore, it must comply with Coulomb's law. If I have two of these magnetic monopoles, the force between them is in accordance with Coulomb's law.
Well, you might want to take a look and see if there's a magnetic charge equivalent of a magnetic charge. You'll see how it enters into all the basic formulas of electrodynamics.
I think you're avoiding answering the question, but anyway.
Well, probably I don't know the answer if you really want to know.
Okay, so who thinks that magnetic monopoles exist or don't exist.
Depends on what the
Based on this
definition of it
discussion.
is. Depends on what you mean by that. You know, that's kind of what I've been trying to get at. I think it depends on what you mean.
Well, it certainly exists as a concept.
Well, my point was that I was just talking about with Bill was that the concept of a magnetic pole it basically goes back to Coulomb. Okay. And so if you accept the idea of a magnetic pole according to Coulomb, then the idea of a magnetic monopole is just a redefinition of magnetic pole.
Well, I mean, I think a monopole would be a situation where you would genuinely only see, say, the South Pole being detected, and there is no even hidden opposite pole anywhere in the system. So the key operational thing is anywhere in the system that you are observing. So, for example, I would not consider two magnets that have the similar poles glued to each other be a monopole, even though you could take a compass and you could probe all around that thing, and you would see only the South Pole, because the North Pole is still existent in that system. It's just not exposed on the outside.
I don't think if you do that, you should be able to do that experiment yourself, Franklin, and I think you will find that the magnet will demonstrate both the north and the south, even when you have them glued together. You won't find that only the North Pole will ever be pointed to by the compass. But you should try that one yourself. I'm sure you'll find that that's not the case. You can't eliminate the pole by just gluing them together.
Well, if you
you can have things that look like that. Right.
If you go online and
But
look for
you can't even
unipole
do that
magnets, you'll
with
find them
electric
for sale.
charge. There's no such thing as an electric charge that's isolated. There's always going to be the opposite charge. You can't have a isolated positive charge. It just doesn't exist. There's always,
Well,
it's always going to have a negative charge that it terminates on someplace.
no, you can have an isolated positive charge. That's definitely, you can have that.
How are you going to do that?
Well, you just take like an electron. That's definitely a single negative point, and you can probe all around it, and it only has negative field coming out of it.
Where does the field go to?
It goes out.
And where does it terminate?
Doesn't terminate anywhere. See, now the thing is that magnetic fields terminate. Magnetic fields
somewhere.
No, magnetic fields terminate.
No,
That's the difference between electric and magnetic fields, I feel, is that magnetic fields always have to terminate.
No. What you said is wrong. It's false. You can separate an electron from an atom, but that creates a positive charge someplace else, right?
Only because most of the matter in the universe is in fact neutral.
Debating the argument.
No, I would say that they're different because a magnet, the poles can't be, say, arbitrarily separated like they can in an electron, a positron. But although I kind of see your point, but but I don't consider things like this. See, this is my monopole. So all it is a wood block where I have glued all of the north poles to the inside, and this is my other monopole, which I painted black to distinguish it, where I've done the opposite. And so if you were to probe this, you would find that, no matter what orientation you do it to, it's going to react like, the South Pole. Although I don't know, if I go in the corner here, then as Cornelius said, maybe you'll see that it's not quite 100%. But if I were to make like a whole, like basketball-sized thing of like this, then it would probably be very difficult to see the edges of the magnet at that point, right? So you can probably see the edge of the magnets in this little square. But if I made a basketball-sized one, then probably it would look very much like a magnetic monopole. But in my opinion, that's cheating because the magnetic field is still on the inside.
That's a cool demo. Do you have two red ones?
I have two red ones, and they always repel. Say they always. There's no way you can make.
At the corners, try the corners. Try the corners on them. Do they repel at the corners too?
They don't strongly attract, but you can kind of feel repelling forces as you get to the corners and stuff like that. So you can kind of make it stick like that way.
No matter what you do, you can't get them to stick together.
Well, not because of the force of gravity. I mean, I suppose if I
do they stick together normally in any configuration?
Well, in a sideways configuration, they'll like this. They will stick together if you go side to side because of the side of the magnets will stick.
So that's a monopole with holes.
Yeah, it's a monopole with holes, but that's kind of how you. And based on I've seen most of Bill's stuff, and most of what he's doing is building these monopoles out of regular magnets by orientating them, by either putting steel plates between them or gluing them together, or some other mechanical manipulation. So he's starting out with things which have two poles. And I think whenever you do that, whenever the thing that you're I don't care how you make the so-called monopole. If you're starting with things which have poles, then that's not a monopole. That would just be my opinion.
Well,
That's a nice demo. Nice demo. I like the fact that you make it for less than $10.
The point is that you have to have magnetic poles to create a monopole. So that's what you just said, right?
No, I'm saying that if you would have a true monopole, you would not make it out of things which originally had poles. So show me making a monopole out of something that didn't.
So the real issue of a definition of a monopole is it has to be an isolated magnetic source.
Yeah, an isolated magnetic source, not a superposition of polar magnetic sources.
Right, but we also know that doesn't exist for a charge. So.
Well, I'll let you have that point, but I feel that
magnetic monopole. Magnetic monopole is going to be a charge. It's the same as an electron, negative or positive charge, because it's going to behave exactly the same.
Well, this brings up the whole question. We were kind of getting so we're about an hour and a half, but I think what is the relationship between the magnetic field and the charge field, right? Those two appear to be completely distinct, but there seems to be a close relationship between those, but what is that relationship, right?
Well,
so all we know.
Covariance says that the equations for the electric field and the magnetic field should be identical but different. In other words, there's two distinct equations, but they have the form of the equation, the operators and everything in it are all identical. That's what was done, why they like the using the vector potential and the scalar potential in doing Maxwell's equations, because they satisfied a similar equation, mathematical equation. And that's where this idea of covariance and it's kind of a symmetry idea came about. And so if you have magnetic monopoles, you can't show the covariance through the vector potential and the scalar potential approach. You have to just use the electric and magnetic field as the basic entities, and everything is made from the fields instead of the charges that are creating the fields. But that's something you have to see. You have to look at the experimental results that were done and see if you agree with the concept that the most fundamental thing is the field, not the particle. And of course, in current theory of elementary particles, the standard model of elementary particles, the idea is the particle's the most fundamental thing, and it creates fields around the particle, and that's all the fields there are. But when we look out in space, we see there's a lot more fields you could account for on that basis. And so then the question is, well, what is producing these currents that are going to galaxies and providing the energy for the sun to run and various stars? Where is that energy coming from? And it's coming from the fields. And so that's the question is to well, is the field more fundamental than the particles?
Well, let's talk about that. So, what's fundamental? So you have presented the two possibilities. Number one, the field itself is fundamental. Okay, so that whatever the magnetic, well, let's say the electric field, because I think it's easier to understand electric field. So let's say the electric field is fundamental. But then if the electric field is fundamental, then what is the magnetic field? Is that also fundamental?
Well,
let's
say the truth. Let's say gravitational field is fundamental.
And is that a different field?
The gravitational
you can
field.
Ask that question, but I have derived the force of gravity from the electric and magnetic fields by solving the empirical equations of electrodynamics, and I get more terms in the gravitational field, and I can explain that we don't need dark matter or dark energy, and I can explain the quantization of gravity, all from the fact that it's due to the fields, the vibrational fields of systems that are solitons of the electromagnetic field. And so that's very interesting because no one in the past that I know of has ever been able to explain dark matter and dark energy as being just due to the force, the electromagnetic force. And
no one in the past has ever been able.
The force of gravity was discovered by chemists, and they were the first to show that
well, what is the fundamental field? I mean, if you're saying the field is fundamental, then is it the electric field which is fundamental?
The electromagnetic field, there's no distinction between the two parts.
Mm-hmm.
Okay, so Bill says that the electromagnetic field is fundamental and that gravity is made out of the electromagnetic field.
Yeah, I'm of a very similar opinion, although I don't call it that. Electromagnetic field. I would say that the gravitation is fundamental, and from that you can build the electrical. But but they're basically the same field. They're different geometries of a wave action within the field. Is that so? Is that correct, Bill?
I think there's some equivalence there. It's a matter of what do you call it? Your nomenclature, and and what really shocked me was when I found that 3,000 years ago, that was the understanding of natural philosophers, and we have reinterpreted what they said to fit what we think today. But for instance, the idea of the atom was referring to the monad, which is smaller than what we would call the chemical atom today, and smaller than an elementary particle, smaller than a nucleus. And and that's the approach that I'm trying to show. And I've had some success with the theory of elementary particles by showing the monad structure of the various elementary particles. And I've been able to predict all their decay modes, their properties, and their mass. So
now let's get back to
that, Bill. Is the monad then your constituent matter or constituent existence of a physical field?
It's a soliton of the electromagnetic field.
Okay, but
soliton is a long-lived property of any fluid. Fluids can have solitons, but the electromagnetic field, the soliton can have a lifetime of the age of the universe, whereas in a liquid like water or air or something like that.
So Bill, is the electromagnetic field a fluid?
It fits the properties of a fluid, yes.
Yeah.
And in standard politically correct science, the electromagnetic field is considered a fluid.
Okay,
fluids
material? Dynamics.
Are not all fluids material?
Well, you can say that, but how can the structures of the electromagnetic field be stronger than any known material, any known particle? In other words, when Winston Bostick made solitons, he was going to use them to make a bottle to contain controlled thermonuclear fusion, because no known man-made material can withstand that without crumbling over time. And that's the problem with controlled thermonuclear fusion. So he showed that the soliton was stronger than any atom or nucleus or elementary particle known.
Yeah, but we're getting down to the chicken and egg thing. You say that electromagnetic field is fundamental, which means it can't be broken down into anything, but yet you say the electromagnetic field acts as a fluid,
yeah,
which as in our familiar world is made out of material particles. It's particulate, actually.
Well,
so to make it
laws
not
of fluid
fundamental,
dynamics don't depend on that.
I think they do.
Well, for instance, the soliton, the structure of the soliton, you can do it with smoke and air. You can
which are all made out of
you
particles.
can do it in water, but
It's all made out of matter
but they don't
particles.
have a long lifetime. In other words, the lifetime of a smoke ring, a toroidal ring, is minutes.
Yeah, but you can understand that the crux of the problem here is that if the fundamental magnetic field obeys hydrodynamic laws, that the hydrodynamic laws require a medium.
Yeah, the problem with the soliton, with the hydrodynamic and fluid characteristic is if the field is a fluid characteristic, it doesn't support transverse waves. And transverse is what light is.
Oh, well, I would question whether can you show me an actual experiment that shows light as a transverse wave? If it's transverse, it's going up and down. Can you measure the wave height of the transverse wave?
Transverse is in seismology, transverse waves do not travel through a fluid, and they do travel through the solid of the earth. That's how they discover oil wells and oil pools and liquid.
Yes, and you can measure the transverse displacement. I'm saying that I keep on challenging people. I keep on challenging people. I keep on challenging people who think that light is a transverse wave to show me an experiment that actually shows it. There are no experiments that shows that light's a transverse wave.
What about grading?
Not broomsticks being thrown through a picket fence either, Brett.
Yeah, that I believe is an extremely naive interpretation of light waves.
It's one you gave.
Well, that's because I'm showing that's
polarization.
Yeah, that's polarization.
Right,
I mean, but typically the transverse wave is like a rope through a picket fence, and that's what I'm saying is just all I'm saying that if you think light is transverse, prove it.
You use a grating.
All I'm saying is that basically transverse waves
double slits can do it.
No, none of those things show that the light is transverse.
Yes, it does. Because longitudinal light won't produce the patterns that you see when you have transverse.
No, you're going circular there. You're saying that all we know is what light does, right? Now that none of that can really prove whether it's transverse or longitudinal.
Well, let's put it this way: a solid is the only thing that will support both transverse waves and longitudinal waves.
That's true. Now the thing is I'm saying that light is not.
If transverse waves can exist in any form whatsoever, then there must be a solid foundation for them to begin with.
Yeah, and I'm saying that light is not a transverse phenomenon.
Otherwise,
transverse they don't.
Simply would not exist in this world.
And generally they don't.
But they do exist.
They exist in solids. They do not exist in light. That's my argument.
So what you did is you made a liquid from a solid, or a solid from a liquid.
No, I've eliminated light as being a transverse phenomenon.
Oh, I doubt that.
Like I said, if give me an experiment to prove that light, show me the transverse component, the actual transverse component. measure what the wave height is.
Bill
You
just
can't
did
do
it.
it.
that with a-
Bill just did it. He
with
said it was
experiment.
polarization.
You can do
No,
it with a grating.
polarization does not prove transverse transmission.
No,
It can
but
be done with longitudinal waves.
you longitudinal waves will not produce a pattern going through a double slit or a grating like transverse waves in light. And you can do the same thing in water. You can show the same.
Bill, if light is a transverse wave, it has a translational motion up and down. You should be able to measure that in centimeters. So for a red laser light, what is the wave height that it is
You can
transverse
measure
in?
the wave height by just doing a double slit experiment.
Then what is it?
Just change your width, change your separation of the slits, and you'll find out a formula, and you can measure it.
No, you're measuring wavelength, not wave height.
You're also measuring wave height based on a surface, like a water wave or a wave in a rope. We're talking
Yes.
about a wave that's traveling through a solid medium, like a transverse wave that travels through the Earth when they do seismological studies, which has no limited amplitude. The amplitude diminishes vertically as well as just like the amplitude of a longitudinal wave diminishes radially.
That still doesn't
But it
prove
does
that
not
light
have
is a
but
transverse.
it does not have a finite, definite height. When
If
you
it's a
travel through,
transverse
it only
wave,
has a
it has a definite height.
it only has a finite height when you create that wave on a boundary condition like the surface of the water or a rope or something like that, which limits its height.
So may I suggest this? You know, when it comes to the longitudinal and the transversal waves, so we have to distinguish between two different kinds of media. So ideal fluid, so no friction, no compressibility, and say gaseous fluid, non-ideal, with viscosity and compressibility. So in the first one, there is no way to have transversal waves unless on the boundaries, as somebody just mentioned.
Correct.
Other kind of media, within it's the same media, you will have both waves. Now, how you are going to detect this or that, this is another issue. So, regarding the previous discussions about, electromagnetic fields and then the smoke ring and so on, I think it would be very much helpful if we imagine some area or some volume exactly with full with smoke, tobacco smoke under high pressure, and then create those smoke rings and see what's going on. That would be really kind of good emulation, proper emulation of what ether substrate would be. And then I come to the to Bill Lucas kind of insights and have discussion and so on. Of course, I would be able to offer some amendments. But regarding the transversal and the longitudinal, that's really things should be that clear. I mean, that depends on the medium, and if medium is not it has these limits, and then you have another area, another medium like water and air. Then what you have here, for example, if water is totally incompressible and viscoseless, you would have inside water only longitudinal waves, but on the surface of the water you will have the transversal ones. Do you agree with that? I mean, that would be simple. Or every how I say
media requirement.
every how say mechanical engineer. You know, do you remember this story with Tesla? When people were thinking of ether as non-compressible and viscoseless, he had said there is no way to have transversal wave there, and then everybody was, kind of was doing boo at him, right? And then, of course, you can say, okay, there is no longitudinal waves or transversal waves in ether, even if it is ideal. But on the boundaries, on the antenna, bordering antenna, things like that, then you will have something like manifest as transversal. And then, Tesla was right, right? And now, if ether is gaseous substrate with viscosity and compressibility, then everything can become clear. We have viscosity, we have compressibility, we have everything. Non-zero divergence of B, D, A.
The thing about a transversal wave,
Everything. We have just to free ourselves of those kind of constraints.
the thing about a transversal wave is although it travels in a solid, it requires a boundary condition to be initialized. And you will not find light emanating from anywhere other than a mass, and the mass is the source of the boundary condition.
Well, I mean, the only way that, because I personally thought that transverse waves could not exist except under the boundary conditions. But if you thought of an infinite set of balls and springs, just have a ball in the center, then springs heading out towards your neighbors in an infinite expanse. So you could think of a transverse wave. In that case, if I just grabbed a hold of one of those balls and I shook it up and down, then that would cause a transverse wave to travel through that medium without there being a boundary, actually. So that's the only way I can think of it.
What would be the amplitude?
There is no friction. There is no way to produce
just a minute. What would be the amplitude in that transversal wave now?
The amplitude would be.
What would be the peak heights?
The wave height is when you grab the ball and you lifted it up and then you slammed it down. That would be the wave height. However high you lifted it up and put it back down where it was, that's the wave height.
Andrew, Franklin, because you've also affected the balls above where you're lifting it and below where you're lifting it.
Below, yes.
Okay, so the balls above where you're lifting it are getting closer together as well, right?
Yes,
they are. So the peak of that wave is not where you're lifting it. The peak of that wave could be well above that because there
is no peak of the wave.
There you go. You answered your own question. There is no amplitude to a longitude to a transverse wave.
No, there's still a displacement. I mean, if you get particle A in there and you displace it, you can measure that. I mean, it's not a peak, but there is a displacement that's measurable.
That's correct. There's a maximum differential displacement between the balls, but the differential displacement between the balls diminishes as you get farther and farther away from where you are displacing the main ball that you're hanging on to. So there is really no peak or no end to that wave in the transverse direction. And that you were asking, what is the amplitude of that wave? In a case of a solid spring arrangement like you're talking about, there is no peak. It's a diminishing strength vertically.
Well, at any point,
that answers your question that there is no amplitude. What amplitude?
No. At any point, if the wave is traveling, perpendicular to the displacement, at any point you should be able to measure the displacement, and you should be able to do that.
You should, but you also look at the balls above that where you're measuring that, and they're also displaced.
And they will also have a displacement. So they do have a displacement. They do have a displacement.
There is no finite peak. Okay.
No, there is not. Well, I'm just saying that there's maybe I spoke wrong, but I'm just talking about that there's a measurable displacement in a direction which is perpendicular to the direction of travel.
You understand?
That's the thing I say that can't be measured because it doesn't exist.
Question here, Franklin. I got a question for you. Is a wave on the surface of the water transverse or not?
Yes, that's a transverse wave.
Okay, but I got a physics book that says
it's a combination.
It's both a transverse and a longitudinal wave, according to my book here.
It could be. I mean, perhaps the only true transverse wave you can have is the rope that you wave up and down, right?
Well, as long as you can concentrate on the surface of the water, you're only looking at transverse.
Yeah, because
I think this whole thing is kind of a question of definitions.
No, because you asked about a wave on the surface of the water. If you're looking at the motion of the molecules, other than the individual molecules that form the surface, the individual molecules that form the surface only move in a transverse direction.
Okay, well, it looks
Correct.
like we're at the top of the hour
Wow.
here. So we're going to have to close things up. But
That's not necessarily true.
so
Okay.
let me see if I can summarize a bit here. So we were continuing our discussion on the magnetic force, and we motivated Hans to add his Lorentz force to his Hilbert book model project. So I have a link to it on this slide here to derive what the Lorentz force is. But then we had some discussion from Bill Lucas saying that none of those equations take into account magnetic monopoles. And then there was just like raging amounts of doubt as to whether magnetic monopoles exist. So Bill gave us a link to a demonstration of the magnetic monopole, and we watched that. And next time when I'm showing a video and you guys can't see it, please scream loudly so that I can know that you can't see it, right? So that I can change it so you can see it. In any case, so we watched that video, and it mysteriously showed something which looked a lot like a magnetic monopole. And there's a discussion about whether is this fake news or is this something that's real? I personally think that this demonstration was completely fake and was done using magnets which are oriented on different axes. So we weren't actually looking at the same magnets all the time, and the video has various suspicious looking cuts in it, and a lot of these things could have been faked.
Franklin, is the link here in this list? The link to magnetic monopole demonstration.
Yeah, that's the YouTube, but like Bill says, you just search for magnetic monopole on YouTube, you'll probably find it. So there's some question as to whether that YouTube video is fake or not. If it's fake, that guy went through a lot of trouble. If it's real, someone needs to go find some liquid nitrogen and either confirm or deny this claims. I mean, I would be personally very surprised if that actually worked that way. But in any case, Bill has offered to send papers on his magnetic monopole. So just send him a email, drop him an email, and then he'll send you his paper. Then we began discussing what is fundamental here. So Bill believes the electromagnetic field is fundamental, and that say gravity is made out of the electromagnetic field. But then we kind of get into the chicken and the egg thing, where if the electromagnetic field acts as a fluid, as it would if an electron is like a smoke ring kind of structure, and that fluid would have to be made out of particulate medium. But then finally we got into discussion that if the medium is particulate, would it